Welcome back to Nanoindenter training. I have replaced the glass Petri dish that I used for calibration with my sample. My sample is also a Petri dish, and coated on the bottom is the sample I want to look at. I have filled that Petri dish also with the liquid I want to make my measurement in, and my tip is sitting just above the surface of the liquid. I can use the dials on either side of the instrument to bring the tip down so that it's just above the surface of the liquid. But now I want to make sure that the tip is submerged under the liquid, but still far away from the surface of the sample. I'm going to do this kind of cautiously, so I'm going to move in 300 micron steps, and I'm going to start to move down. And by eye, I'm just looking to see when the tip hits the liquid. It is just hit. I'm going to make it go down maybe 2 more times. I'm still very far away from the surface of the sample, and I can tell just by looking at it from the side. If I did need to make any XY adjustments to my sample position, I could do that with these arrow buttons to move the sample in any direction. But it looks like right now I'm still fairly centered over my sample. The next thing I want to do is find the surface. You remember earlier I showed you under options, there's a find surface tab, and in there, there's this Z above surface. So after I find the surface, it's going to pull off the surface 5 microns. So let's go ahead and do that. And as you do, you will see that at the top, it says finding contact. At the bottom, there are various things that are active. And we can also see this tip starting to move closer to our surface. When it does make contact, you may see a little blip in the green curve. We'll watch for that. There we go. That was the little blip right there. And when it finishes, you can see it says idle, and at the bottom, there's nothing that's active. So now I should have my tip sitting about 5 microns above the surface of the sample. I'm going to run a single indent. So I'm going to come into this configure experiment tab, and I'm going to load the program I wrote earlier, which was a single indent. And I'm going to double check that this looks the way I want it to. Actually, for this first one, I may start with 800 nanometers of indent and just see what that looks like. And save. And it's going to ask me if I want to overwrite. I'm going to say yes. And then I'm just going to hit this run experiment button. And you can kind of watch in real time what's going on down here. I may have to blow this up. There is our curve in terms of as a function of time. This is also as a function of time. So if we look at this scan up here, the blue curve is the piezo. So that's the only thing it can really control. The green curve is the tip or the cantilever. That's the one thing that it really can measure. And then the red curve is derived from the difference between the two. And that red curve is how much you're actually indenting into the sample. If we look at this curve over here, this is maybe more similar to what you're used to seeing. This is a force versus indentation curve. The blue portion is the approach. There is sometimes a dark blue region where it kind of holds, and then the green is when it's pulling back off of the surface. The red is our fit to the data. And this looks like a decent curve. I may run one more, but I want to move to a new location. So I'm going to raise the tip up 300 microns. I'm going to move over 300 microns, and I'm going to find the surface again. Again, we can see that it's active because there are things at the bottom and at the top that are telling us that it's doing something. It has just found the surface, and so I can run that experiment again. You can see that we have some movement of the piezo, and then it's hard to see on this scale, but a little bit of movement of the tip as well. And again, a decent curve. So a lot of times, even if I'm planning on running a matrix, I will run a few single indents just to make sure that things are appropriate and the settings are where I want them to be. Now, one thing you'll notice is that I have indented maybe 1,200 nanometers, maybe even a little bit more than that. I asked for 800. It will very commonly overshoot. And so I'm going to now run a matrix scan, but I am going to reduce my indent because I know it's going to overshoot. So let's configure this experiment. We're going to come back to the folder. I saved all those programs, and now I'm going to run this matrix scan. For the sake of training, I'm just going to do it 2 by 2 just to make it kind of quick. And I'm only going to make it 100 microns between the data points. And I want to start right where I am right now. So I'm going to say use stage positions. So it imports my current stage positions. I'm going to move up 300 microns before I move in XY. And then after I find the surface, back up 5 microns. I think that should work. In the profile, I'm going to make this, yeah, I want to keep it at 500. The last one I did was at 800, so I want to do 500 instead and see what that looks like. But otherwise, this looks good. So I'm going to hit save. Yes, I'm going to overwrite. And I'm going to run the experiment. So it is right now finding the surface. And it just found that surface. And now it's going to start my indent. And I may zoom in on this so we can see it a little bit better. And there's my first curve. It just moved to the new location, and now it's finding the surface at that new location. Just found it, and now it's starting my indent. So you can see that if you have a relatively well-behaved sample, you can take a decent amount of data in a fairly automated fashion, which is great, especially since a lot of biological samples will show a decent amount of reproducibility, or you will show a decent amount of variation in the samples. And so in order to get reproducible results, you're going to need a decent number of curves and be able to average your modulus values and so on. Now, while it's taking that data, at the bottom, it is extracting Young's modulus for us from these fits. So you kind of get a feel for what your modulus is as you're going. These are pretty close to 1 kilopascal, looks like. And I think this is our final scan. We can control the amount of the curve that it's fitting during this automated fitting routine. And I'll show that to you right now. So under options, under the first part of options, there is a percent of the curve. We are using a Hertz model to fit this data, and I'm fitting 80% of the curve. But if you know, I realize that every time it's overshooting, like this curve is still going about 1,200 nanometers into the sample. Maybe I only want to fit, you know, the first half of it. So maybe I change that to 50%. Now I think that's going to apply to all the future scans. But we also have data analysis software that I'll show you in the next video that allows us to change it and get those values. So you can see that these measurements are relatively easy to do and to set up. And if your sample is well behaved, you can take a lot of data relatively easily. Thanks for joining me.